going to start today's WFNR webinar. So good morning or good afternoon, everyone. I'm Won-Suk Kim from Seoul National University Bundang Hospital, South Korea. Today, WFNR Research Committee invites the distinguished speaker and the panelist for the lecture of Basic Parametric Test. The speaker is Adriana Conforto from Brazil, and she is a neurologist, professor, chief of the stroke group and of the neurostimulation laboratory at the School of Medicine, São Paulo University, and also researcher and professor of the postgraduate program at Albert Einstein Hospital. She invited Professor Raimundo Soares de Azevedo Neto to participate of the Q&A at the end of this webinar. He is an associate professor of the medical informatics lab in the pathology department at the School of Medicine, São Paulo University. So during or after the pre-recorded lecture, please feel free to leave your questions in Q&A chat. So now let's listen to Dr. Conforto's lecture. Christian, please play the pre-recorded video. Thank you.
Hello, my name is Adriana Conforto. I'm a neurologist. I'm chief of the stroke group and neurostimulation laboratory at Hospital das Clínicas, São Paulo University, and also a researcher at Hospital Albert Einstein in São Paulo, Brazil. We're going to talk about basic parametric tests. These are my disclosures. So we'll start with an introduction about types of variables and hypothesis testing. Then we'll move to the question, when should I use a parametric test? We'll talk about t-tests and one-way analysis of variance, or ANOVA, which are basic parametric tests. And then at the end, we'll finish with the choice of a statistical test. So starting with types of variables. Variables can be qualitative or quantitative. Qualitative variables can be classified in nominal and ordinal. So in nominal variables, there is not an order between categories. So we have, for instance, different eye colors. There is not a particular order or types of ranks between different eye colors. Or we can have ordinal variables in which there is a particular order, and the values can be ranked. So an example of a qualitative nominal variable that we can use in a rehabilitation study, for instance, in a clinical trial in which we have group A, an intervention group, and group B, a control group. So there is not a particular order between the two groups. So we can consider group as a nominal value, variable. On the other hand, for an ordinal variable, we can show the modified ranking scale. So this is a scale of disability and is often used in stroke studies. And modified ranking scale, or MRS, of 0 means that person has no symptoms. Then with increasing scores, the disability gets progressively worse. And with an MRS of 6, the person is dead. So there is an order, but the differences between the consecutive categories, they do not have the same meaning. So an MRS of 0 to go from an MRS of 0 to an MRS of 1 does not have the same meaning of going from an MRS of 4 to an MRS of 5, or from an MRS of 5 to an MRS of 6. So there is an order, but the information of the difference between the two consecutive categories of the scale, the information is different. So this is an ordinal variable. There are different ways to analyze ordinal variables. An example is to take the percentage of subjects who have an MRS score of 0 to 2, depending on your research question, And you may want to compare the percentages of patients who reach this MRS from 0 to 2 after a given intervention compared to a control intervention. Quantitative variables, they can be discrete when the data are discontinuous. So we have a countable number of integer values. An example is the number of people. You cannot have 1.5 person or 1.56 people. So this is an example of a discrete quantitative variable. On the other hand, if you measure strength, you may have a continuous variable. So you can get any value in an interval, and the number of decimal places will vary according to your instrument. So this is a continuous variable. Now that we talked about variables, we'll briefly review hypothesis testing. So the procedures that we use to reject or not the hypothesis and the probability that this could be purely by chance. So let's say we have to decide if a person is guilty or not guilty of a crime. In the first example, the truth is that the person is not guilty, and this is our null hypothesis, or H0. Then our verdict is that the person is guilty. So in this case, we should have not rejected the null hypothesis, but we rejected the null hypothesis. So we incur in a type 1 error, and an innocent person goes to prison. On the other hand, if our verdict is that the person is not guilty, so we do not reject the null hypothesis, we are making the correct decision. If the person is guilty and our verdict is that person is guilty, again, we make the correct decision. But if the person is guilty and our verdict is that person is not guilty, we incur in a type 2 error. So we did not reject the null hypothesis when we should have rejected it. And the level of significance, or alpha, often set to 0.05 or 5%, is the probability of rejecting the alternative hypothesis when it is actually true. Statistical power is the probability that the test will reject the null hypothesis when the alternative hypothesis is true. So for a given level of significance, the bigger the sample size, the lower the probability of type 2 error, and the greater the power. So after we briefly reviewed these topics, we are going to talk about the statistical tests. So how can we use objective procedures to reject or not a hypothesis? We have to remember that the statistical tests, these procedures, they have associated statistical models. So they are valid under certain conditions. And in order to apply them, we need to assume that conditions of a particular model are met. So when should I use a parametric test? So some assumptions in order to use these tests are there. First, we have a continuous variable, and we already know what this means, that there is normality and there is independence of observations. So talking about normality, so here we have a normal or bell-shaped curve. We have the mean here in the center, so the mean and the median, they are in the same position in this curve. We have most of the values within these 2 standard deviations above or below the mean. So here in this area, we have around 68% of the values within 2 more or less standard deviations, we have around 95%. And within 3 standard deviations, we have around 99%. And so if we build a histogram, we can see what a histogram of a normal or Gaussian distribution would look like. But we perform research and rehabilitation. We collect biological real data. So the distribution of the data does not have to follow or to fit perfectly a normal distribution. But in order to use a parametric test, it has to be at least close to a normal distribution. And how can we know that? So first, it's very useful to visually inspect the data. So if you have a big sample size, you may not need to run a test for normality, but it's always nice, it's always interesting to visually check the distribution of your data. So you can build a histogram, and let's say if you have this type of histogram, you can see that it's not perfect, but it's close enough to the histogram that we have from this data here, from which we have a normal distribution. On the other hand, here on the right, we can see the histogram of skewed data. So we don't have small amounts of data here at the extremities. We have skewed data that, and then we cannot accept the assumption of normality. Another way to look at this is by using box plots. So here in this box plot, we see the mean in the middle, and we see symmetric whiskers. So they have the same size, these 2 whiskers. On the other hand, here and here, we have whiskers of different sizes or asymmetric, and we do not have normal distributions. And finally, another way is to use a QQ plot or the quantile plot. So the quantiles are the values which divide the distribution such that there is a given proportion of observations below the quantile. So let's say we divide the distribution in 4 parts. We may have 4 quartiles. If we divide the distribution in 100 parts, we will have percentiles. And so in the QQ plot, here in the x values, we have theoretical quantiles, and then y-axis, we have the sample quantile. So we try to correlate this to these quantiles and check if there is an overlap between the theoretical and the sample quantiles. And here, it's fair to say that this is true. On the other hand, here on the right, we can see that there are many values here in this quantiles, and also here, there is not a good overlap between these 2 lines, and then we do not assume a normal distribution. So depending on your sample size, if you feel like you need to test for normality, there are different tests you can use, for instance, the Shapiro-Wilk or the Kolmogorov-Smirnov. So the null hypothesis for these tests is that the distribution of the data does not differ from a normal distribution. In other words, the data set can be well modeled by a normal distribution. So if you apply one of these tests and the p-value you get is lower than 0.05, then you have to reject this null hypothesis. And in this case, you do not assume a normal distribution. So using these QR codes, you can access rehabilitation manuscripts that provide examples of using these tests to check for normality. So the Kolmogorov-Smirnov or the Shapiro-Wilk. This is an example of the output that you can get from a statistical program that you use to check for normality. So in this case, the Shapiro-Wilk test, because you have a p-value higher than 0.05, you can consider that you can assume a normal distribution, and you reject the null hypothesis, and you do not reject the null hypothesis. You assume that there is that you can use you can assume a normal distribution, or that your data can be modeled in a way that because their distribution is close enough to a normal distribution. So here, if you want to get normally distributed data, you will wish your p-value to be higher than 0.05. If it's less than 0.05, you cannot assume a normal distribution, and you cannot use a parametric test. So there are other tests that can be used in that situation. So depending on your sample size, you may want to run this kind of test to check the assumption of normality. But if the data are not normal, you can go to a non-parametric test, but parametric tests, they usually have more power. So you can test your hypothesis with more power with a slightly smaller sample size. So you may prefer to use a parametric test. So a possibility to do that if your data are not normally distributed is to perform a logarithmic transformation. So you can take the log of your values, or the log of the value plus 1, then you run the normality test, also do the visual inspection, run the test for normality. If the transformed data are normal, then you check for the other assumptions, and if they are met, you can run the parametric test and the log transformed data. And finally, the independence of observations. What does this mean? So when the observations are independent, the score which is assigned to any case must not bias the score which is assigned to any other case. So let's say you have two groups, A and B. You have 4 subjects, two subjects per group, and you have 5 measurements from subject 1, 2, 3, and 4. You can see that the measurements from this single subject, they are closer to each other than they are to the values obtained for subject 2 or subject 3 or subject 4. So these values here, they're correlated, but their result, if you designed your project well, if you performed your experiments in an unbiased way, so the values that you get for one subject do not interfere in the values that you have for another subject. So the measurements are independent across subjects. The measurements from one subject do not bias the measurements for the other subject. So this is independence. So given these assumptions are met, we may want to use t-tests. So t-tests were described in a paper by William Gosset in 1908. So Gosset was a chemist and a mathematician, and he worked in a brewery, actually in Guinness. And the scientists who worked in Guinness, they were required, if they published papers, not to use their real names. They couldn't disclose their names. They could not disclose their place of work, so that they worked in the brewery. And that's why Gosset used the pseudonym student, and that these tests became known as the students' t-tests. So the t-tests were envisioned to compare means when the sample sizes were not big enough. So the first example is the one-sided, the one-sample t-test. So when you want to compare the mean from a sample with the mean in a population. So you draw a sample from a population, you know the mean from the population, and you want to compare the mean of your sample with the mean from the population. So this is not usual in rehabilitation research, but it's one type of t-test. So the formula for this statistic to calculate the t-score is the ratio between the differences between the two means and the standard error. The standard error is the standard deviation divided by the square root of n. So this is the sample size. So you want to know if your mean, the mean of your sample, is significantly different from the mean in the population or not. So if your mean is falling here in this part of the distribution, or here, and then it's less likely that it is equal or not significantly different from the mean of the population. So in this case, you can reject the null hypothesis if your hypothesis that the means are equal. But if you fall within this region here, you cannot reject the null hypothesis. You can have two different approaches to the problem. So you may want to know whether this mean is significantly lower than the population mean, and then you can use a one-tailed t-test. You're just going to compare here and all the rest. Or you can want to know that whether the mean is higher than the population mean, and then just compare here and here. Or you can test, you can ask a different question. Are the means different? So the sample mean can be either smaller or bigger than the population mean, and in that case, you're going to use a two-tailed test. You're going to make the comparison here and here. So depending on your question, you may choose a one-tailed or a two-tailed test. And we use typically programs to run the t-tests, but you may also want to run it manually just to understand how it's done. So you can calculate the t-score with that formula that was shown before. And then you go to a t-table. So this t-table is going to show critical t-values that you are going to use to know if you can reject or not the null hypothesis. So let's say you have 12 subjects, and you have then 11 degrees of freedom. So the degrees of freedom are the sample size, or n minus 1. And that you choose a p-value of 0.05 or 5% for a one-tailed test. So you're just going to compare this with all this. So for a one-tailed test with a p-value of 0.05, the critical value for 11 degrees of freedom is 1.796. So this means that if your t-score is higher than 1.796, you can reject the null hypothesis. If your t-value is lower, then you cannot reject the null hypothesis with a significance level or an alpha of 5%. But you probably use a program that will give you the t-score and the p-value. So this one sample t-test, like I said before, is not very usual in our type of research, but something that may be more common is to compare to independent populations. So let's say you have two groups again, A and B. You want to compare their means. You have to check that whether the distribution can be assumed to be normal and the observations are independent. So if so, in these two independent groups, you can run an unpaired t-test. So here's the formula. So you're going to have the ratio between the difference of the means and the standard error of the mean differences. A large t-score is going to indicate that there is a bigger difference between the groups, and the smaller the t-score, the more similar are the means. A t-score of 5 indicates that the groups are 5 times as different from each other, or their means are 5 times different as they are within each other. So there is another issue if you're going to check for differences between the groups with an independent t-test or an unpaired t-test. You may want to check whether the variances can be considered equal or homogeneous or not. So if the variances are homogeneous, you are going to consider that the variances are equal. If not, you're going to use a Welch's t-test. So what are different variances? So this is an example of homogeneity of variance or homoscedasticity. So here we have two groups. You can see that the mean values are going to be differences, but the variance, the spread away from the mean is pretty similar in the two cases. So the distances between the values, they are not very big. They are homogeneously distributed in the two groups. On the other hand, here on the left, we have unequal variances. So here we have a bigger variance. The distances between the values, they are not constant as they are here. They're not similar here as they are here. So in this case, you cannot assume homoscedasticity, and in this case here, you can assume because the two groups have similar variances. But then again, this is a visual way to show this. How can you test for homoscedasticity? You can use, for instance, the Levene's test. So the null hypothesis is that the samples have equal variances, and the alternative hypothesis is that the samples do not have equal variances. So you come up with the W statistic. Here is the formula. And let's say just a situation in which you might want to apply this type of test, of unpaired t-test. let's say you have, again, our two groups, A and B. You want to measure a score in a given scale, and you want to see if at baseline, the scores between the groups are comparable. Or let's say you're measuring the scores at baseline and 1 month after a given treatment, and you're calculating the difference in score before and after treatment. And if you want to know if these differences in scores, these changes in scores are different between groups A and B or not, then the way to enter the data, so it depends on the program that you choose, and there are many tutorials available for different programs. But as an example, you could put in one column the group. So 1 stands for group A and 2 for group B. Here I'm showing an incomplete set of data, so it's preferable for an unpaired t-test that the two groups have the same number of subjects. This is not mandatory, but the test is more robust when the sizes of the two groups are the same. And here you include the data. So in each line, there is the value of each subject. And what you put here in this A column tells from which group the subject belongs to. Then you run the test. Here, let's say you do not have a sample size that is big enough. You want to test for normality, and then you use the Shapiro-Wilk. Your p-values for both groups are higher than 0.05, so you assume normality. Then you test for equality of variances. The p-value of your Levene's test is also higher than 0.05, so you assume that the variances are homogeneous. Then you run the independent sample score unpaired t-test. And this is the student t-test with a p-value of 0.001, which you can use because you assumed that the variances were equal. If the variances had not been equal, you might want to use the Welch test. And again, with both tests, you have a p-value of less than 0.05. If that was the significance level or the alpha that you chose, you can reject the null hypothesis, and you're going to conclude that the means between the two groups can be considered to be significantly different at the significance level. Then let's say instead of comparing means from two groups, you want to check what happens in one group. So let's say you provide a treatment and you want to compare the scores at baseline with the scores at 1 month post-treatment in the same patients. So you're going to perform within subject comparisons, within group comparisons. And as long as the measurements for one subject do not affect the measurements of the other subject, you can say that there is independence, that the assumption of the independence has been met. This is the formula for the paired t-statistic. Again, ratio between differences in means, now in means of pairs, divided by the standard error of the mean differences. So the null hypothesis is that the pairwise difference is 0. So patients assessed before and after one intervention. Let's say again we have that. Now we will have just one group of patients, and we'll call A the measures performed at the group of measurements performed at baseline, and B the group of measurements performed after treatment. So again, depending on the program, the layout may be different, but an example would be now to include here in the A column, the data at baseline. So each line represents one subject, and in the B column, the values obtained after treatment. Again, the output of this will depend on the program, but for instance, here you have your test of normality, the result, then you assume normality, then you run your paired t-test, and you get here this p-value of lower than 0.001, and you reject the null hypothesis, so you conclude that there is a difference from baseline to after treatment in this particular score. Now, finally, another situation when we have 3 or more groups. One idea would be to run lots of t-tests between each pair of groups, but this is not the choice that you should do. It's better in this case if you have values from 3 or more groups to run an analysis of variance or ANOVA. In this case, if you have one measurement in each per subject per group, you're going to run a one-way ANOVA. So the analysis of variance uses an F-test. So basically, you compare means, you compare variability within the group with the variability across the groups. So the null hypothesis is that populations have equal means. If the null hypothesis is rejected, you then run post hoc tests. So with the ANOVA, you should not use the pairwise comparisons because you are going to incur in a family-wise error of performing multiple comparisons. And why does this happen? So let's say you have not 3, but 4 groups, A, B, C, and D. And for each comparison, A versus B, A versus C, you have a 95% no type 1 error. So the probability of not having a type 1 error is not 95% if you set an alpha of 5% of 0.05. Assuming that each test was independent, the overall probability of type 1 error will be the multiplication of all these probabilities, and the result will be 0.735. So you have a much bigger risk of incurring in a type 1 error. So in order to avoid this family-wise error, if you have 3 or more groups, you should use analysis of variance as long as the assumptions for the ANOVA are met. And then after you have the result of your global test, of your ANOVA, you have your value of F and your p-value. If this result is statistically significant, then you're going to look for the differences between pairs of groups with post hoc tests. There are different post hoc tests that can be used. You can choose depending on your goal. You can be more or less conservative. And so it's nice for you to take a look at these kinds of tests after the talk. So if you have 3 or more independent samples, again, you have to check for the assumptions, normal distribution, independent observations, and whether the variances can be considered homogeneous or not. So supposing that the variances were considered to be homogeneous, You run first your one-way ANOVA. Here is your F, here is your P. So if your alpha was 0.05, here your p-value is less than 0.05, it's actually less than 0.001, then you go to run your post hoc test. So do not run this post hoc tests if you did not get a significant result when you ran the ANOVA. But then in this case, we had a statistically significant difference. Then we go for the post hoc tests between groups A and B, A and C, and B and C. And we only got, using the Tukey test, significant differences between groups A and C and B and C, but not between A and B. So this is important because you want to know where the difference was found. So in addition to the general ANOVA, you have to perform this kind of analysis. And finally, we are reaching the end of the talk. So how are we going to choose the statistical test? First, very important, it has to be clear to you what is your research question. What comparison do you want to make? What is the question that you want to answer? Then you define the types of your variables, their numbers, and you check the characteristics of your data. So depending on whether your research question is to independent groups or you want to do within subject comparisons, or whether you have more than 2 independent groups, you can choose one of those basic tests. For other types of designs, for instance, let's say you want to make measurements in 2 groups, A and B, at baseline and 1 month post-treatment. Then you may need to use more complex models, such as repeated measures ANOVA. You may want to use other general linear models, but there are other options too. So this is not the goal today. We're just really going to review this parametric, this basic parametric tests, but you should know that there are a lot of options out there for other different types of questions. So for the type of variable, you're going to look at your design, then you check the number of variables, and in terms of characteristics of the data, whether you have independent observations or not, whether you can assume a normal distribution or not, and whether or not you can consider that the variances are homogeneous if this is required by the particular parametric test that you're going to use. So reviewing for 2 independent groups, if all those assumptions are met, you can use independent t-tests. If they're not met, there are other options of non-parametric tests. If you have 2 related groups of data, so like before and after treatment, the assumptions are met, you have paired samples t-test. If they are not, you have also non-parametric options. And if you have 3 or more independent groups, one-way ANOVA. If not, also you may have other options. The advantages of the parametric tests, like we said before, the main advantage is the bigger power, but the parametric tests often rely on more extensive assumptions and on the existence of a normal distribution. The non-parametric tests, they may have less power, but they are distribution free. So in terms of references, to study more about this, there are some manuscripts that you can access with these QR codes and some books for suggestions. I'd like to thank you for your attention and thank also colleagues who helped with suggestions for this presentation. Thank you.
Dealing with some important issues in basic parametric test and introducing some examples in the neurorehabilitation research. And it's also my first time to know the story behind the student t-test. It was interesting. So now we don't have any questions from audience yet, because I think statistics is always difficult. So now I want to ask some questions. So in case of some ordinal variables, such as manual muscle power test or a modified actual scale in our neurorehabilitation research, I sometimes find the paper using the mean rather than median. So is it the right way to present the descriptive statistics for ordinal variables with the mean rather than median? So it's my question, simple question.
So no, so with an ordinal variable, you can use the median, but not the mean, because the values between each consecutive point in the scale, each category, they're not constant. So then you should not use this measure. So maybe, I don't know, if Professor Raimundo would like to add something. And I also like to ask Professor Raimundo maybe to comment on p-values, that sometimes they're overrated, but there are also other important information that we need to check. And if possible, if we still have time, to comment a little bit about confidence intervals.
Hello, everybody. Thank you for the invitation. Well, the first question by Dr. Kim, it's difficult to say it's wrong. I don't like to say it's wrong to use this or that parameter. So the mean is very common. It's easier to understand than the median in general. When you are presenting results, it's a good idea to present both, perhaps, because you can compare when the mean and the median are close from each other in terms of value. It suggests that the distribution is symmetrical. So the symmetry of a distribution brings the mean and the median values very close. And when you present both values, then you give the reader from your results more information about the distribution in this case. So that I wouldn't say it's wrong to use the mean, but it's better to use the median when you have ordinal values or ordinal variables. Okay? Okay. I guess it's okay. I mean, does the answer attend your question?
Yes, thank you. So I agree with you. And then for the categorical variables or some ordinal variables, I agree with that, using median and the interquartile range for presenting the result. And then also, yes, I agree with you. And also it is a good way to also present the mean if we can. So there are one, yeah.
Sorry. Yeah, I think, for instance, for the MRS, which was, I think, the question, like that, you don't have an MRS of 1.5 or 2.5. Yeah. So yeah, if you take the mean, you may end up with an MRS of 2.8 or 2.5. And so I think it should not be really the best choice. Sometimes we see that, but it's better, I think, to not to make it too confusing, to use the median in this case. Just that sometimes the mean is, like Professor Raimund said, is very used, it's easier to understand, but then it may lead to some values that do not really exist in this case.
Yeah, thank you. And we have one question, so it's similar with me. So would you allow using a parametric test? For example, modified ranking scale, which are categorized as a non-parametric data. So can you answer it, Professor Adriana?
I think it's very similar. So usually a way to analyze the MRS is to look at the percentage of subjects who have an MRS between given values, let's say 0 and 2 or 0, 3. There's also a possibility of making an ordinal analysis of the MRS. Because let's say you include in your study patients who had, let's say if it's a stroke study and you have patients who had previous strokes and they don't start with an MRS of 0 before the stroke. So they have the disability from that stroke and also previous disability from a prior lesion. So maybe if you only categorize percentages of subjects with an MRS of 0 to 2, you not look at the shift in the ranking score that can occur with the treatment. So you can make a shift analysis and to see if, even though instead of just dichotomizing the scores in 0 to 2 or 3 to 6, you can see if there's a slide in let's say if there is a change in 1 point or a change in 2 points, and that's meaningful. But in terms of using parametric tests, I think it would not be recommended overall, because it's not a quantitative continuous variable. So when you run a parametric test, you have to base yourself on some assumptions that model will be appropriate for the kind of data you're analyzing, and it's not really the case for an MRS. So usually what you see in the literature is either this dichotomized analysis or this shift analysis, but not the parametric tests.
Yeah, thank you. So Dr. Raimundo, do you have any comments on that?
Just to call attention that in the literature, when you are reading papers, it's very common, it's a very common mistake to run t-tests or ANOVA tests for ordinal variables or any indicated numbers, even for quantitative discrete variables, because discrete variables must be proved to have normal distribution before you use t-tests. So it's easy to run a non-parametric test as well as a parametric test, and it's better to follow or to check the assumptions before you use any test. So really, you will find many mistakes in the literature, and this is bad because you learn by reading papers as well. So when you read papers, you follow the methods you find in papers. So this is bad.
Yeah, it's a valuable comment. And then we have one more question. It's also similar. So what do you think of using minimally clinically important difference in tests like a modified Ashworth scale? So it's the same question maybe. So Dr. Adriana, so
I think this is a great question, because this is a very important concept. So sometimes you can have statistically significant differences. And I mean, I said during the talk that I was choosing a p-value of 0.05, but that's a choice. You can choose a p-value of 0.01 or 1%. So that really is something arbitrary, that it's a decision that you make. But then let's say, regardless of the p-value that you chose, that you found that there was a statistically significant result. It doesn't mean that that difference is clinically meaningful. So then you have to judge whether that difference that you found was of sufficient magnitude in order to be clinically meaningful. So in regard to the modified Ashworth scale or any other scale, whenever possible, you should also try to interpret the results and think about whether that difference is clinically important. And for some scales, it may be the minimal clinically important difference may be not well established. So there's more work to do, but for some, there are some values that have been defined by different studies, and it's something that you can look at. Actually, in that last slide that I have where I put the references, the last paper on the right is a paper from 2014 from Page that specifically addresses the role of assessing minimal clinically important differences, and also about checking and building confidence intervals instead of just going for the p-value and thinking that this is it and you know, stopping there. You really have to interpret your results. And then also there are other measures of magnitudes of differences that are very valuable for us to be able to interpret the evidence. So I'd like to invite you to read this paper. It's focused on rehabilitation, and it clarifies many concepts that are important for us to interpret this type of result.
Just to reinforce this idea, we have to look at the clinical significance in every subject you are treating. You have to understand that our goal is to improve health, or in rehabilitations, very important to see how are you improving functionality, let's say. So the numbers are just an instrument, a way to measure, but they don't mean absolutely everything. You have to look at the clinical significance, not only the statistical significance. And there are some complementary measurements like the effect size you can use to represent in a way the clinical significance. So there is a fallacy in statistical techniques that if you enlarge the number of the sample, if you use, let's say, 1,000 of people in a sample, you may get easily a statistical significance, but the result is very, very little in terms of the clinical efficacy or efficiency of what you are treating. So just to say, remember, you are in the health science, not in the number sciences only. Numbers are instruments for us to compare. They make it easy to compare, but they are not the final answer. And the p-value is just one of the parameters to look at, not the only one. That's it. Thanks.
Thank you for valuable advice, and then thank you for detailed explanation and the references. So we don't have further questions. So now 7:05 here in LA. So I think now it's time to wrap up today's webinar. So this webinar will be uploaded at WFNR homepage, and so you and your colleagues can freely access. The next webinar will be held February 10th with the title of Prediction for Stroke Rehab. So I really appreciate Professor Comforter and Raimundo and the audiences for nice lecture and the valuable questions and comments. So have a good day, and then goodbye, everyone. See you on next webinar. Bye.
Bye-bye. Thanks very much.
Thank you. Bye-bye.
Bye.
Bye-bye.